Okay, the decibel, current and voltage dividers, electrical power calculations, sine wave, root mean square values, and peak envelope power calculations. A 2 times increase or decrease in power results in a change of how many decibels? Approximately 3 decibels is the decibel change for a half power or a doubling of power. The decibel scale is a logarithmic scale, and unless you're familiar with logarithms and comfortable with them, it won't make a lick of sense to you. So just remember that a 2 times increase or decrease, either doubling the power or cutting the power in half, is approximately 3 decibels of change. Now, decibels are a ratio. So if we cut the power in half, we talk about a loss of 3 dB. If we increase the power, if we double the power, we talk about a gain of 3 dB. But decibels, as you see it here, just 3 dB, is a ratio. It's a comparison of 2 powers. It's not an absolute unit of measurement. How does the total current relate to the individual currents in each branch of a parallel circuit? It equals the sum of the currents through each branch. So here I've got a branch circuit with parallel resistors in it, and the total current going through this wire here is going to be the sum of the current going through here, plus here, plus here, plus here. Okay? So in a parallel circuit, the total current equals the sum of the currents through each branch. How many watts of electrical power are used if 400 volts DC is supplied to an 800 ohm load? Now, when you did the technician test, you possibly had some of these, and when you studied for technician, you had some of these. This throws a little bit of a twist into it. You'll remember, correct answer is 200 watts. We'll get that on the table right away. You'll remember you had these two relationships, okay? We had the pie chart, the power formula, which said P, power in watts, is equal to current times volts. Okay, and then this is Ohm's law, which says volts is equal to current times resistance. Okay, now what they've done to us in this question doesn't allow us to use either one of these. We have to use both of them because they're asking us for power if we have volts and resistance. And this formula here doesn't give us resistance. So we have to go to here to find out what the resistance is, and then we can come back to here to find out the power. So we want to find power, but we don't know what the current is. So in the other formula, we find current by going I, and to use this, you cover up the one you want, and this tells you that you find that by dividing this by this. Okay, if you're the one above is divided by the one below. Okay, or if the one you want to know is this one, then it's I times R. Right. In this case, we're going to have we have the voltage, and we know the resistance. So the current is the one we don't know. If we divide the 400 volts by the 800 ohms, we find that we have half an amp. Okay, now we know the current, so we can go in here to the power formula, and we know that the power in watts is equal to the current in amps times the electromotive force in volts. So now we have P is equal to 0.5 times 400 volts. Half an amp times 400 volts is 200 watts. This answer right here. Okay. This is for somebody who's not going to use it all the time. You can remember these two, and you can work through it in 2 steps like that. For someone who uses it more, they have all of the relationships charted out like this. Now, let me tell you something. Even the electronic technicians and engineers that use this don't have it memorized. They'll have it on the workbench or something, or up on the wall or something like that. But you're not going to have that option in the test. So, but what this does show us is here we can do it in a single formula power is equal to the voltage squared divided by the resistance. Okay, if we do that, then power is equal to 400 times 400, the voltage squared, divided by the resistance of 800 ohms. 400 times 400 is 160,000, divided by 800 is 200 watts. Okay, so that's how you can find the answer to that. Okay, how many watts of electrical power are used by a 12-volt DC light bulb that draws 0.2 of an amp, 0.2 amp? It's 2.4 watts, and here you can use just this single formula. The power is the current times the voltage, or the 0.2 amps times the 12 volts is 2.4 watts. So to find power, we multiply the ones that are uncovered there, I times E. How many watts are dissipated when a current of 7 milliamperes flows through 1.25 kiloohms? Okay, well, that's cool. What do those words mean? Okay, let's take a look here. Okay, you want to know the power, but you don't know the voltage. You can find the voltage using this formula here, E equals I times R, but before you can do that, you have to convert the units because they've given them to you in milliamperes instead of amperes and kiloohms instead of ohms. And for this to work, you have to reduce it to the basic units of volts, ohms, and amps. Okay, so first you have to convert your units. So we know that 7 milliamperes is 0.007 of an amp, and 1.25 kiloohms is equal to 1,250 ohms. Okay, so now we can put those into this formula, and we can say that the E, the voltage, is the 0.007 amps times the 1,250 ohms, and that shows us that the voltage is 8.75 volts. Okay, now we can go to the power formula, and we can use our amps again, times our 8.75 volts, and we get 0.06125 watts, and when we change that to milliwatts for our answer up there, we get 61.25 milliwatts, or approximately 61 milliwatts. Again, that can be done this way, using these formulas. First, you have to convert your units again. Now we're going to use the formula power is equal to the resistance times the current squared. Okay, and if we work that out on the calculator, 1250 times 0.007 times 0.007 is equal to 0.06125. 0.06125 watts is 61.25 milliwatts. Okay, so again, we arrive at the same answer that way. Okay, I moved question G5. I moved question 6 to later in the group because there are some more definitions here that you need before it's going to make any sense to you at all. So we'll skip it for the moment, and we'll come back to it before we finish this group. Which value of an AC signal results in the same power dissipation as a DC voltage of the same power? This is called the RMS value. And here's what we're talking about. Here we have an alternating current signal, okay, and it's changing. It's a moving target here. It is going to its maximum positive value. This dimension here represents time, okay, and through time it is going to its positive value, back to 0, to its maximum negative value, back to 0, and it continues doing that, okay? Now, as you can see, if we had direct current, we would have a current here that remains stable above the 0 line. But with alternating current, we don't have that. And to figure out what the actual power dissipation, or the heating value, is one way of thinking of it, of the alternating current would be, we have to find this voltage right here, which is the root mean square voltage, RMS voltage. Okay? And for a sine wave of this shape, the RMS voltage is the peak voltage multiplied by 0.707. So it's about 7/10 of the peak voltage for a wave of this shape. Okay? The RMS value is the value of an AC signal that results in the same power dissipation as a DC voltage of the same value. What's the peak-to-peak voltage of a sine wave that has an RMS voltage of 120 volts? Okay, let's look at the picture. And this is throwing another little curve at us here. But let's start with 120 volts. We have an RMS of 120 volts. That's this one right here, 120 volts AC. Okay? Now, before we can find the peak-to-peak, and the peak-to-peak is from this peak to this peak. Okay? Before we can find that, we have to find this peak. And to find that peak, we're going to take the RMS voltage, and we're going to multiply it by 1.414. So that voltage, the peak voltage there is going to be 169.7 volts. Here's 169.7 volts. The peak-to-peak voltage is twice that. So the distance from here to here is twice 169.7, or 339.4, this answer here. What's the RMS voltage of a sine wave with a value of 17 volts peak? Okay, you've seen the picture. You have you want to know, you have a voltage that has a 17 volt peak, and you want to know what the RMS of it is. See if you can take a look at those various values there and figure out what it is before I give it to you. This one is half of the 17 volts. This one is more than half but less than the 17. This is more than the 17, and this is twice the 17. Which one's it going to be? Okay, it's going to be the 12 volts. The 17 times 0.707 is going to be 12 volts. So you have a 17 volt peak here, and your RMS voltage is 7/10 of that, or 12 volts. What percentage of power loss would result from a transmission line loss of 1 dB? They've thrown a dB in here. I don't know why they put these in the order they do, but this is how they fall. A loss of 1 dB is about a loss of 20%, about a fifth of your power, if you have a transmission line loss of 1 dB. What's the ratio of peak envelope power to average power for an unmodulated carrier? Okay, we're talking here about an radio frequency carrier wave, and this is just almost a definitional thing. The key here is that it is not modulated. So the average power is not varying with any kind of modulation. And the ratio of the peak envelope power to the average power for an unmodulated carrier is 1.0. In other words, they are the same. Peak envelope power is the same as the average power for an unmodulated carrier. Okay? And I can't draw you a picture that will show you that. All I can do is tell you that they are the same as each other. And if you get this question, the answer is 1.0. Okay, what would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? Now, here we're talking about an alternating current. We want to know the RMS voltage, and we have a dummy load that which is the same as a resistor. A dummy load is a resistor, okay, and it's dissipating 1200 watts. Okay. Using a formula from here, the voltage, which is what we're looking for, is the square root of the power times the resistance. We know the power is 1200 watts. We know the resistance is 50 ohms. We multiply the two of those. We take the square root of that, and it's 245 volts. Okay, and we have found this formula here by looking over here in volts, and we see that volts is equal to the square root of the power times the resistance. Okay, so we took the power, we took the resistance, we multiplied them together, and we found the square root, 245 volts. Okay, what's the output PEP of an unmodulated carrier if an average reading watt meter connected to the transmitter output indicates 1060 watts? Now, what did I tell you the relationship was between an unmodulated carrier and average power? It's a ratio of 1.0, isn't it? It's the same thing. So your 160 watts on your average reading watt meter means you have an unmodulated carrier of 1060 watts. Okay, here we are at number 6 now. You have some additional ammunition in your arsenal here to deal with this question. What's the output PEP from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter output? Okay, let's take a look at what we're going to have to do here. We need to find the RMS. To do watts, we have to find the RMS voltage. And to find the RMS voltage, we have to go from the 200 peak to peak. We have to take it to 100 peak. Okay? And with 100 peak, we know that we multiply that times 0.707. So our RMS voltage is 70.7. Okay, we can get our power formula here. To do that, we can look over here and we can see power in watts is equal to the voltage squared divided by the resistance, because those are the values that we have here, is the voltage and the resistance. So we square the voltages, 70.7 times 70.7. We divide that by the 50 ohms. That gives us 4998 divided by 50, which is 99.96, which is really close to 100 watts. Okay, here's a similar question with just different values to it. In fact, it's an identical question with different values. Okay, we're going to do the same thing. This time we have 500 volts peak to peak. And so the peak will be 250, half of the peak to peak, 250. We take the 250 volts, we multiply it by 0.707, and we have RMS voltage of 177. Okay? And we use that same formula. Power is equal to the square of the voltage divided by the resistance. So we have 177 times 177 divided by 50. That equals 31,329 divided by 50, which is 626.58, which is real close to 625 watts.